So I'll be delighted to hand over to your presenters for the evening, Alison and Charlie. Alison.
Thank you very much, Patrick. Yeah, really great to see so many of you joining. What I'm going to do is I'm going to share my screen with you. I'm not sharing slides today because everything that we're going to show you is on the NRICH website. So hopefully over the course of the next hour and a half, as well as showing you some problems and telling you some of the things that Charlie and I like about these problems, we'll also be able to show you a bit about how to navigate the NRICH site so that you can find the resources that we're sharing today. So you may have seen this problem before, the first one that we'd like to look at, which is called 7 squares, because hopefully this is one of the ones that was sent to you in an email before the event for you to have a look at. And so 7 squares is slightly different take on the classic matchstick problems that are often used to introduce patterns and sequences in maths lessons. And if you haven't had a chance to do so, I really would suggest that you have a look at the 3 videos in this problem after today's session, because it shows 3 different ways of thinking about the matchstick pattern at the top and the algebra that it leads to. But what we're going to do is we're actually going to scroll down below these videos, because another thing about this particular task 7 squares is that it has lots and lots of different patterns in it. So I'll just show you a couple of those. So there's the growing rectangles pattern, there's the L shapes pattern here, there's a 2 squares pattern. And so if this problem captures your imagination, there are lots more aspects to it than what we're going to look at during today's session. There's dots and more dots, and there's the rectangle of dots at the bottom. But this is the one that we're particularly interested in, this square of squares pattern. So I'm just going to give everybody a chance to have a look at that and to read through what the question says. And then Charlie, I think it would be good to talk about how we would tackle this problem, but also to invite people to contribute in the chat if they have different ways of looking at the problem that don't crop up for me and you. So we've got a pattern which it says it has side length 5. What do you think it means by that, Charlie?
Okay, hello everybody. So side length 5 means if I look along any of the edges, I can count 5 squares.
Okay, and so there's 2 things that it asked us to explore: the number of edge squares and the number of lines needed to draw the pattern. What would you like to start with?
I think number of squares is going to be a lot easier than the number of lines.
Okay, so it's asked us to look at side length 25, 100 and n. I think I kind of want to start with a side length 5 just to ease ourselves into the problem. So if everybody would like to think about how they would count the number of squares around the edge of this pattern, and you might want to just pop in the chat the way that you worked it out. And Charlie, how did you work out the number of, well, first of all, how many squares do you think there are in the pattern shown on the screen with a side length of 5?
Okay, I think there are 16 squares.
16 squares, okay. And how did you work out those 16? Did you just count them, or did you do something clever?
I would presume to say that it was clever, but I counted 5 squares at the top, 5 squares at the bottom.
Okay, so 5 at the top and 5 at the bottom.
And then I looked at the 2 sort of columns on the edges, and I'd already counted the squares at the top and bottom. And so they only had 3 squares on each side that I hadn't counted.
So you did 5 plus 5 plus 3 plus 3, is that right?
Yes.
Okay, I did it slightly differently. So I looked at the sort of the rotational symmetry of the pattern, and I said that there were 4 squares there, 4 squares there, 4 squares there, and then 4 squares going up like that. So I'm sort of counting those 4, but then this one on the end is part of the column of 4, and then this one at the bottom is part of the row of 4 along the bottom, and then this one here is part of the row up the side. And I can see in the chat some people are starting to share some other ways as well. I quite like this one that's coming from a couple of people that's been suggested. So Lorna said 25 minus 9, and Isabel said 5 squared minus 3 squared, which I can see is 25 minus 9. Where do you think the 25 and the 9 are coming from in this?
So the 25 is the 5 squared, which is, imagine that there wasn't a hole in the middle, so to speak.
So I've just drawn in the lines that would show that the whole thing would be a 5 by 5 square.
And then I subtract the 3 by 3 squared inside.
So that I get that blank bit. So that's actually 3 different methods there. So the 5, 5, 3 and 3, the 4, 4, 4 and 4. And then we also had 5 squared minus 3 squared. I wonder if it's possible to extend each of these methods for a side length of 25 instead. So what would your method look like if we had a side length of 20? Do you want to do 25 or do you want to skip straight to 100?
Well, I'm tempted to think that 100 might be easier in terms of, yes, let's go straight to 100.
Okay, I thought you were going to say 100 might be easier, so let's do 25 and give ourselves a challenge. Let's go on to 100 then. So for the 100 by 100, what would your method look like?
So my original method, I would imagine there'd be 100 squares along the top, 100 squares along the bottom, and then 98 along the edges, because I've already counted the ones at the top. So
okay, so altogether that's going to be
396.
396. Okay, so I think for my method, if it was 100 by 100, each of those 4 sides, the whole thing would be 100, but I'm not counting the end one because I'm sort of wrapping that round the next corner. So I think I'm going to have 99, 99, 99, and 99.
And in your method, each corner is included in one of the lines, but
yes,
only one corner.
Yes. So that's going to give me 396 as well. What about the squared method that a couple of people suggested? How will I work that out?
So it'll be 100 squared, and inside there'll be a 98 squared to take away.
Oh, I might need to use a calculator for that one. 100 squared, take away 98 squared. I'm hoping the answer is going to be 396. Shall I just do it on my calculator? 100 squared, take away 98 squared. It is 396. That's quite reassuring, isn't it? Do you think we can have a go at the one with n then? So I think what I need to do is I need to I'll get rid of the 100 example so I can do some writing down for the n, but I want to keep the 5 by 5 there because that's sort of what I'm referring back to for each of the 3 methods.
Because I remember when we wrote this, Alison, and one of the things that we wanted to do was avoid students just doing a table of values where they went for a size 5 and then size 6 and then size 7, just noticed patterns. And by jumping from 5 to 25 to 100, it might make we're hoping it makes it more likely that they're going to have conversations just like the ones that we're having, where they look at the structure of the pattern, they think about the squares. Dave Hewitt wrote an article called Train Spotter's Paradise, where he was worried that too many people were just looking at number patterns and not looking at what the original context was.
Yeah, so, and certainly that's what I remember from when I first started learning about sequences way back in rather too many years ago when I was in about year 8 or so, we would draw out what the first 5 patterns looked like, or the first 6 patterns if we're feeling really special, and then we would draw a table of results, and then we would look to see what the pattern was, and then we would write down an nth term rule from that. So I think it's quite different from what we're looking at today, and this way of getting into the sequences. So what does your method look like then, Charlie, for the n by n square, the pattern with side length n?
Okay. Can I just add one other thing, because you talked about maybe going to the algebraic side length n, and it feels to me like all the thinking that we've done so far is algebraic, in that the generalizing aspect of algebra. Or the only thing that we haven't done is the algebraic notation.
Yeah, it feels like what Tim Rowland's written about the idea of proof by generic example. It feels as if we've used 100 as a generic example for what these patterns look like as they grow, but now moving from the 100 to the n just doesn't feel like such a big step, as if we'd gone straight to the n at the very beginning.
Yes, so I'm reasonably, I'm very confident that the next step it actually is the easy step. So for side length n, using my method, I'm imagining n squares along the top, n squares along the bottom, and because I've counted the top and the bottom of the vertical sort of columns, it's going to be n minus 2 on either side.
And then I need to do a little bit of simplification there, because I need to know what these 4 numbers add up to. But I can see that I've got n plus n minus 2 plus n minus 2. So I've got 4n, and then I've got minus 2 lots of 2. So I've got 4n minus 4 as my rule there. So I think for mine, I knew that when I had a 5 by 5 square, I was counting 4 lots of 4. For my 100 by 100, I had 4 lots of 99. So for my n by n, I think I can just write straight away that my nth term rule will be 4 lots of n minus 1.
And I can see why it is that, because every straight edge that I have is going to contribute one of the squares, but not both. Sorry, one of the corners, but not both.
So I guess another way of looking at it would be that it's 4 times n, but then take away the 4 corners that you've counted twice.
Yes.
So this is actually rather nice, because it's showing justification for why expanding the bracket of 4n minus 1 gives you the answer of 4n minus 4.
Yes.
It's difficult to say brackets when you're talking, isn't it? There's one last method that we need to look at then, which is the squares method. So what will I write for my 5 squared minus 3 squared method?
Oh, I'm going to have n squared, and inside it I'm going to have an n minus 2 squared, because it's going to be 2 narrower, 2 shorter, because I'm taking one from each side and one from top and bottom. And of course, the manipulation here becomes much trickier.
Yeah, so if I hadn't met the idea of multiplying out a quadratic bracket yet, it might be a little bit harder to see why this is equivalent to the ones that we've already got. But for students who had met this, I think it's rather lovely to be able to say that n squared minus, and then I've got n squared minus 4n plus 4 there. And then when I subtract it, I'm getting n squared minus n squared plus 4n minus 4, and so these bits are going to disappear, and I'm getting the same simplification. And yeah, that's exactly what Fatima's just said in the chat, that once we simplify it, we get exactly the same expression, even though we had different ways of working it out. And that's quite comforting, actually. Have we got time to look at the other?
Add something else? Because we might be put off using that expression with younger students. I know we're going to talk about the mapping document later, and this appears as a year 8 problem. It seems to me that even if students can't do that final step that you did to show that the algebraic expressions are the same, they could still substitute values into 4n minus 4 and into n squared minus n minus 2 all squared and get the same value. So that would be reassuring, and it's not a proof that it's the same, but it means that at least they can express algebraically what they can see, which is a really valuable step. And even though they can't manipulate that yet, I mean, sometimes we say to students, look, in a year or two, we will show you how to multiply this kind of thing out.
Yeah.
And it's preparing them for what's going to come. But they can still make use of it. So like we did, when n is 100, what would you get? Well, we get 100 squared minus 98 squared.
Yeah, Graham's just pointed out in the chat that this is the difference of two squares, and it reminds me of another Enrich problem called hollow squares, which we've actually got as a way of introducing the idea of the difference of two squares for slightly older students. So it is such an important idea, and it's really nice to show it in this very sort of diagrammatic, almost geometric way, rather than just the pure algebra of it. So there's also, as well as asking us to find the number of edge squares, there's the number of lines. And when we were looking at this problem before, I was a bit reluctant because I think it's harder to count the lines than it is to count the squares here. But you've convinced me that we should have a quick look at that. Before that, though, I just want to address Lorna's question, which is what happens when you put in n equals 1 to this. I think to do that, it's quite nice to work backwards from the 5 by 5 example. So the 4 by 4 example would have a 2 by 2 square in the middle. The 3 by 3 would have a 1 by 1 in the middle. The 2 by 2 would have nothing in the middle. And so if I try to draw this picture for a 1 by 1, I would have to be able to draw a negative square in the middle. So I think we would say that this is a pattern where the pattern doesn't make sense for n to be equal to 1, because I can't then continue the pattern there. So that's a lovely question to explore, and to show how each of the different representations of it would start going into negative numbers there. So let me just rub that out. So you convinced me that we ought to look at the number of edge squares. How on earth am I supposed to count the edge squares on this then? The number of lines. Okay,
so one of the things I would do to start with, just to make the problem a little bit more accessible, is to think about the horizontal lines and the vertical lines separately.
Okay.
Because I noticed that the number of horizontal and vertical lines must be the same. Because if I rotate that shape by 90 degrees, all the lines that are currently horizontal will become vertical, all the vertical lines will become horizontal, and the shape won't change. So the image I get is going to be the same. Therefore, if I, by swapping the horizontal for vertical and vertical for horizontal, nothing changes. It must be the same number.
Okay, I feel a bit better about it now, because that means I only have to count half the lines rather than all the lines. So for the, should we go straight to the 25 then? So for the 5, you could count the horizontal and vertical lines. How would you count, how would you convince me how many edge lines, how many lines there would be for a side length of 25?
Okay, I think there would be 25 lines along the top, and then 25 lines just below there. So that's, and then
so that's these ones and these ones, yeah?
Then way down, there would be another 2 lots of 25.
Okay.
And there are also some horizontal, so I'm just counting the horizontal ones,
right,
and then I'll double to work out the total. And then there are some horizontal lines.
The sort of in-between ones here.
Yes, and they will, okay, so if I start at the very top, I imagine starting at the very top and finishing at the very bottom, I think there would be 26 lines altogether. It's a bit like
why not 25?
Okay, it's a bit like that fencing problem where you have a 100-meter field and you're going to put posts every 10 meters. How many posts do you need? And everybody the first reaction is to think that you need 10 posts when actually you need 11, because you need one post at sort of the base, 0, and then one at 10, one at 20, one at 30, eventually the last one at 100.
Okay, so I could think of it as counting the top of every square, which would give me 25, but then I haven't counted the bottom of the bottom square, so then that's what makes it 26. So do I have 26 on the left and 26 on the right?
26 minus 4, because I've already counted 2 of the lines at the 25s at the top and the 25s at the bottom. I've already counted those 4.
Okay, so that's down to 22 then, and 22. Okay, while you're adding that up, and then of course that's the horizontal, so I'll need double it for the vertical. I think I've spotted another way of counting this. So I don't know if anyone in the chat has got their own way of counting it, and you want to just drop us a message to see your way of seeing this. But I've just noticed that I can unfold these squares, and instead of having them going round in a line, I can imagine them just stretching off like that. And I know that when I get to the end of that line, this bit here where it joins on, I will have already counted it. So I'm going to end up with a line of squares with an opening at the end. Okay. Now I already know how many squares there'll be, because that was the bit that we worked out before. So I think for 25, my rule was 4 times 25 take away 4. So that would be 96 squares altogether. So I think there'll be 96 squares, and each square, well, I need to be careful here because there are lines that involve both squares, but this is actually like the 7 squares problem at the top of the page. So I think I can think of each square as contributing 3. So every time I draw a new square, I draw this sort of C shape of 3. So I think the answer is 96 times 3, which is 288. What did you get for your method?
Well, the 425s plus the 222s come to 144. And if I double that, because I also need to count the vertical lines, I also get 288.
I think it's, again, it's rather satisfying that we got the same result in 2 different ways. And we could go on to do exactly the same thing for describing the nth term rule in both different ways for this. So yeah, this is a problem that I think we both really like, because we're looking at the structure to explain it. But you can also do something else, which is to say, if I tell you the calculation that I've done, can you suggest to me what I might have done to lead to that calculation? So if I'd told you that I'd worked it out by doing 96 times 3, can you work out where the 3-ness of it is and where the 96-ness of it is? So there's a lot of focusing not just on what the algebraic expression is, but about where it might come from. And I think the second problem that we want to share also looks in that way at looking at the structure of what's going on.
And that's part of getting students to expect the algebra sort of to talk to them. You know, when we see 2n plus 1, we know that that means an even number plus 1. It means it'd be nice for students to feel that structure is hidden in the algebraic expression.
Yeah, I think it also is starting to think about the sense of how a sequence is growing. So when I see something like the 4n minus 4 that we had, I want to know what is it that's making it change by 4 each time I go up by 1. And that's something that I think we're going to look at a little bit later on in one of the other problems that we're going to share. Okay, I want to show the problem steel cables then. So this is what steel cables looks like on Enrich. And the problem starts with a size 5 cable made up from 61 strands. So I just want to give everybody a chance to look at this size 5 cable and to have a think to themselves about how they might convince themselves that there are 61 strands there without counting all of them. And then because it's a little bit difficult in the chat to describe something like that, what we've actually got is we've got some different methods that students have used to solve this problem in the past that we want to share to show people some of the different ways of thinking about it. So I'm just going to stay quiet for a moment to give people a chance to look and to convince themselves of the answer for 61. If you are convinced and you want to think about a follow-up question, there is a suggestion that the next thing you might want to work out is the number of strands needed for a size 10 cable. So don't pop your answer to that one in the chat just yet, because that feels like a bit of a spoiler. But if you want to think about it and work on it, then you can. So just going to give you a moment to think. Okay, just in case people aren't familiar, when you go to a problem on the NRICH site, there's always this little sidebar that has something called Getting Started, which is to suggest to students how they might begin the problem if they're not sure what to do. There's something called the solution, which it's not always there, is it, Charlie? Sometimes it would say submit a solution instead. What is it that governs that?
It depends whether it's a recently created problem that we're currently featuring and we're inviting solutions to. Normally, every half term, we publish a new set of problems, and then we invite solutions. At the end of the half term, we edit those solutions and then they get published.
Okay, so this is one that was published some time ago then, so it means that there's already some solutions there. I'm not going to click on that because I don't want to see any solutions just yet, but I am going to click on the teacher's resources, because I know that in the teacher's resources there is a handout here which is called Steel Cables Methods. I will just show you the templates one, because this is really good if you want to get students to draw on the cable to show how they are seeing the pattern. But the methods sheet has 4 different methods on it, and these were actually taken from a group of students. I think it was a group of students we worked with about 10 years ago now, and we worked on this problem, and they did such beautiful diagrams to show how they were counting up the patterns that we scanned them and turned them into this this worksheet so that other people could see these different methods. So I think what might be nice to do is to go through these methods and talk about the conversations that might happen in the classroom and where the patterns and sequences idea is coming out in this. I can see that a few people have started to share how they worked out the 61, and it would be interesting to know whether any of your methods are the same as any of the methods that we're looking at. I think from the description I can spot some things that will look familiar in a moment. But let's look at this first one. So Charlie, what do you think was going on in this student's head when they were explaining how to work out 61 for this?
Okay, so they've sort of split the steel cable into 4 sections, and they could see that in the top left, you could split it up into a parallelogram with sort of 5 rows of 5. So I think there are 25 strands.
So if I've got 5 rows of 5, I need to do 5 times 5 is 25, yeah?
Yes.
Okay.
And then below that, there's a smaller parallelogram of 4 rows of 4. That yellow one at the bottom will have 16 strands. And then a green one on the right, which is a sort of 4x5 parallelogram, which will have 20 strands.
And so then when I add that all together, I'm going to get 61. Now we could go from here to the size 10 cable, but I know we don't have masses of time this afternoon. Do you think we can jump straight to the N by N, the size N cable?
Yes, I can imagine an n by n steel cable, and I could still have an n by n parallelogram in the top left corner.
Okay, like that.
Yes, and I could also see that the parallelogram that I can fit below is going to be n minus 1 by n minus 1.
So why is it n minus 1 rather than n?
Well, that middle row, which in the diagram has got 9 circles in it, so that middle row will be taken up by the n squared, by the n by n parallelogram.
Ah, so that's included in the red bit, so it can't be in the yellow bit.
Yes.
Okay, so that's going to be n minus 1 by n minus 1. So that's n minus 1 all squared.
And then I can see that there'll be that first line that you drew will be n long for the parallelogram on the right, but it'll only be sort of n minus 1 wide. And so that would be an n by n minus 1 parallelogram.
So I've got a formula then, because my nth term rule is going to be n squared plus n minus 1 squared plus n minus 1. I think I'm starting to see why this is a key stage 4 problem rather than a key stage 3 problem, Charlie.
Yes, I'd want students to be able to simplify that.
So I'm getting n squared plus, and then when I expand that bracket, I'm getting n squared minus 2n plus 1. And then I'm getting n squared minus n. And I've run out of space at the bottom of the screen, but I think that simplifies to, is it 3n squared minus 3n
plus 1.
Plus 1. Okay, well, that's quite nice. Let's have a look at the second method that's on here then. So I'm just going to scroll down a little bit. And I think this is very similar to what Alida has described in the chat. So I can see 5 plus 6 plus 7 plus 8 plus 9 plus 8 plus 7 plus 6 plus 5. And I think it's also very similar to what Anna has described, which is 2 lots of 5 plus 6 plus 7 plus 8 and then the 9. So we're seeing this middle row as sort of breaking the symmetry of what's going on. So how do you think these students then might have taken the example they've got there and deduced an nth term rule from it?
Well, I suppose when we work with students, Alison, you and I often talk about mathematicians being lazy. And what we really mean is finding efficient and elegant ways of doing things that save us time. So I think the way that I'd approach this is put the middle row to one side, just ignore it for the time being.
Okay, I'm just going to put it in brackets to say we're going to come back to that at the end. And I guess that is in what Anna said, that is that plus 9 that's on its own at the end. Yeah.
And then I'm going to look at the section above that and the section below that.
So and this bit here and this bit here.
Yes, and what I notice in the section at the top, as I go down a row, every time I go adding one strand, and when I go down in the bottom half, I always subtract a strand. And so if I can imagine combining the rows in the top half with the rows in the bottom half, I think I'm going to get the total number of strands to be identical. So
it's almost as if you're chopping this bit off and then sticking it on down here. Yeah, like that. And you're putting these 2 tetrahedrons together to make a parallelogram.
Yes.
Okay, let's have a go at doing the algebra to go with that then.
So I think the top row from the top plus the top row from the bottom half will be n plus 2n minus 2.
Okay.
And then the next pairing will be n plus 1 from the top and 2n minus 3 from below.
Okay.
I'm going, and so on until at the end I'm going to get a 2n minus 2 at the top and an n at the bottom.
Okay, so all of these, each of them adds up to 3n minus 2, is that right?
Yes.
So I've got 3n minus 2, and all I need to do is to work out how many times I've got that.
And the number of rows that I'm combining from each half is going to be n minus 1 rows, because I've been ignoring that middle row. So I've got n minus 1. In this case, there would be 4 rows, but in general, there'd be n minus 1 rows.
So it's n minus 1 rows times 3n minus 2 for these paired off rows, or the trapezium becoming the parallelogram. But then I need to go back and remember to count that 2n minus 1 that I've forgotten about.
Yes.
Okay. Should we check that that gives us the same formula?
Yes, it should give us 3n squared minus 3n plus 1, I think we worked out earlier.
So I'm getting 3n squared minus 3n minus 2n plus 2 minus plus 2n minus 1, which simplifies to give 3n squared minus 3n plus 1.
Phew.
So again, we've got that lovely thing of finding the same rule in 2 different ways. Also, I think in Patrick's introduction, he pointed out one of the things we were going to talk about was the idea of purposeful practice. And it really feels that this is an example where we've got purposeful practice of the skill of simplifying expressions, multiplying out brackets, collecting like terms, but it is for a purpose. It is to show that these are the same rules throughout. So even though it might be a lesson on patterns and sequences, we're still practicing those other algebraic skills as part of it.
Earlier, you spoke about having a formula and then asking students to figure out how it is that that formula could have arisen. Here's another example where you could ask students to imagine if there is a way of splitting up the steel cable so that you can see why it's 3n squared minus 3n plus 1. I'm not sure we're going to have time to do that, but everyone at this workshop could go off and think about it later on.
Yeah, it makes me think about the different ways of writing this, because this might seem like a simple way of writing it, but you could express it as being 3n n minus 1 plus 1 instead. And so it may be that some of the ways of expressing the formula make more sense than others, or are easier to explain than others. I'm aware that we are, we've still got quite a lot to get through, but there are 2 more methods to look at. So I think it would be nice to say a little bit about this method, and then to talk about why perhaps the 4th method is structurally the same as this. So I think this might be what, similar to what Nyan's suggested, which is 6 triangles plus the center. So yeah, I can see there 6 triangles plus the center. What might students need to know in order to generalize this formula then?
Well, I suppose each of the triangles there is the 4th triangle number. So if I look at any of those triangles, I can see it's 1 plus 2 plus 3 plus 4.
Okay.
And so that's the 4th triangle number. So I'm going to need the n minus 1th triangle number when I come to n strand steel cable.
Okay, so I'm going to say the formula is 6 times Tn minus 1 plus 1. And then I'm going to hope that you haven't noticed that Tn minus 1 isn't expressed in terms of n. And then you're going to come back to me and say, no, I want to know why this is 3n squared minus 3n plus 1 like the other ones. So there are a couple of lovely problems on NRICH for looking into triangular numbers. And so there's one called Picturing Triangle Numbers, I think it's called, which looks at how you can take the triangle numbers like this and by having two copies of the same thing, so I'm just going to draw the other copy in a different color, you can put one on top of the other upside down, and then you make a rectangle. And so the rectangle's dimensions are n plus 1 and n. So that means that the nth triangular number is n plus 1 divided by 2. And there's also another problem, which is called slick summing, which does this rather than in a graphical way, it does it in a sort of numerical way. So I think it takes the numbers from 1 to 10 and does 1 plus 2 plus all the way up to 10, and then 10 plus 9 plus all the way down to 1, and then works out that you always get 11 when you add these things up, but 10 times 11 would have counted it twice. So you divide by 2 in order to get the 10th triangular number is 110 over 2, which is 55. And I think that's very similar to the method that Carl Friedrich Gauss was supposed to have come up with when he was a schoolboy, and the teacher said, can you add up all the numbers from 1 to 100, thinking I can put my feet up and that will keep them busy for an hour or so. And Gauss put his hand up straight away and said the answer, because he derived the formula in his head at the age of 8. I think that story is probably not true, but it's a nice story anyway.
Before you scroll down, Alison, can you write your 3n squared minus 3n plus 1 again in your factorized form, where you wrote 3n n minus 1 plus 1? And can you do me a favor? Can you just draw a parallelogram made up from the purple triangle and the black triangle that's next to it?
So, like that.
And then another parallelogram, which is made from the green and the purple triangle.
Ah, I see what you're doing here.
And then
so I'm counting my triangles in pairs.
And each parallelogram is an n by n minus 1 parallelogram. And I've got 3 of them, plus so I can see where this formula has come from.
Okay.
All that we've been doing also reminds me about the way that Joe Bowler talks about multiple representations, giving students this very clear message that there isn't just one way of doing things. And I suppose we pride ourselves in coming up with rich tasks, which can be, we look for tasks that can be done in a variety of ways and be understood in a variety of ways. And sometimes we try and find ways, numerical ways, diagrammatic ways, algebraic ways of doing things, and hoping that students will become flexible and not, if one way doesn't work, then they've got other resources that they can draw upon.
Yeah, that's helping to develop resilient problem solvers, but also giving students lots of ways to be successful in maths lessons, because rather than the focus being the correct answer to a problem, the focus is the method used. And so for every different method, there's the opportunity for recognition. I think another problem that we were going to mention that people might like to explore if they've enjoyed this is the problem marbles in a box. And in that, the 4 methods that we've shared with people have got names attached. But one thing that it's rather lovely to do in the classroom is to use the children's names for the methods that they've come up with. So if Zach comes up with a particular way of doing something, then the whole class can talk about doing things using Zach's method. And we had the Phoebe, Alice and Luke's method in the 7 squares problem. So this being able to name methods and conjectures can help to build that sort of classroom culture. The last method then, I think all I really want to say about this is that we've got a ring of 6, a ring of 12 outside that, a ring of 18 outside that, and so on. And so this can then be counted up in the same sort of way, because by taking out the factor of 6, you're getting the triangular numbers to appear again. But I really want to show everybody the sort of the super clever way of taking this up a dimension. So I know we're supposed to have moved on to the next task already.
But I don't want anybody to think that they're being foolish if they didn't think about this method.
No, this is something that I think somebody came up to me when I'd used this problem in a workshop and said, why don't you just do it like this? And it was, well, because I didn't see this until you pointed it out. So they saw this as being a 3-dimensional problem. And they drew in these lines to make a cube. And they said, okay, so I'm seeing it as a 5x5 cube, but it is only the sort of the front and the side and the top of the cube. So there's a 4x4 cube behind, which has sort of been taken out to leave this shell behind. So it's just 5 cubed, take away 4 cubed, which is 125, take away 64, which is 61 as required. And then, of course, they said, if you do n cubed, take away n minus 1 cubed. Multiplying this out might technically be key stage 5 because it's using the binomial theorem. But I think key stage 4 students could have a go at multiplying out these brackets. So I get n cubed minus, and then n cubed minus 3n squared plus 3n minus 1. And so that's then going to give me my 3n squared minus 3n plus 1 when I multiply it all out, which I just think is gorgeous. And yeah, I every time I go through that with anybody, I just think, I wish I'd thought of that. But I can take joy in sharing it. So that was the problem, steel cables. If people want to find this problem, I think the easiest way to find it, you can just type in enrich.maths.org/steel cables. That doesn't work for every problem on the website, but it does for some of our favorite problems that we've bothered to rename. But you can also use the search bar. So if I type in steel cables here, it will bring me up, and you can see it says that there is one matching title, and that takes me to the problem steel cables. You can also find the problem that I just mentioned, which is marbles in a box, and you can do the same thing, and there's a poster for that as well as a problem. But yeah, that's one quick way to get to a problem if you know what its name is. But I think the next problem that
Can I just say, Alison,
yep,
in case people are concerned, I will be writing I will be sending an email to Jane Twine and Vicky Sansom with the links to all the problems that we've talked about today. So please don't worry about remembering exactly how to find these. You'll be getting an email in the next few days with the links to all of them, and they're all freely available. So you'll be able to access all of them. And I'll also put one or two that Alison has referred to that possibly, like picturing triangle numbers and slick summing.
And hollow squares I've written down on my list as well that we mentioned. So
yes, I'll add that to my list.
Brilliant. Okay, so shifting times tables. This was another one that we invited people to have a look at before the session. So some of you might have already had a really good play with this. So again, we've gone back to, this is age 11 to 14 problem. So we're thinking probably, suitable for year 7s, and it's got a challenge level of 1 star, which means it's definitely in the low threshold, high ceiling category. We're thinking that this is something that everyone can have a go at. And I'm going to do exactly what the students do. I'm not going to read any of this because I can see that there's an interactive bit down there. So I'm just going to ignore everything that it says and scroll straight down to the interactive and start clicking on things to have a play around. So what I'm going to do is I'm going to stick with level 1 for now. I'm not going to do what a student did when I used this in a workshop a few years ago, which was to say, oh, I'm going to start with level 4, and then came to me quite sheepishly about 2 minutes later and said, I'm stuck. And I said, why don't you start with level 1 then, until you know what it is that you're supposed to do, and then we'll try the level 4 a little bit later. Okay, so shifting times tables then. So the idea of this then is that when we're introducing the idea of linear sequences, we can talk about the most familiar linear sequences to students. So they already know, hopefully, their times tables. And so we talk about the idea of having a times table and then shifting it up or down. So Charlie, what do you think a student might say to talk through this example to work out what the times table and what the shift might be?
Sorry, I had to unmute myself. Okay, so they might notice, well, the first thing they might notice is that they're all odd numbers. The second thing they might notice might be that there's a difference of 8 amongst all, and so I suppose we're hoping, given the title of this interactivity, that it's got something to do with the 8 times table. And then when I look at the numbers, I notice, they're all 1 less than numbers in the 8 times table, or they're all 7 more than numbers. So 23 can be thought of as 1 less than 24, but it can also be thought of as 7 more than 16.
And the nice thing about the way that this interactivity has been designed is that we can use either of those representations. So I can put that it's the 8 times table shifted up by 7, and it will mark that correct. But I could have also said shifted down by 1, and it marks that as correct as well. And so whereas if I'd got that wrong, but that bit correct, then it tells me that I've got one of them wrong. So it's giving me feedback to help me to decide. Now, I think level 1 is slightly less interesting than level 3 and 4. So can I show you what a level 3 or 4 example is?
Can I just ask Alison, if you'd typed in table 4, shifted down by 1, because all those numbers are 1 less than numbers in the 4 times table.
Okay, so it's not marking that as correct because it says we should always enter the biggest times table that it could be. So although it could be the 4 times table, and it's just not showing us every entry in it, it wants us to go for the biggest possibility there.
Okay.
And the reason that it becomes important is because in level 1 and level 2, it gives us the just 5 consecutive terms from the sequence. So this would be the first 5 terms in a sequence. But if we go on to level 3, you'll notice that this is now just, it's not 5 numbers going up in order. It is 5 seemingly random numbers, but they have all been taken from the same shifted times table. So I'm going to give everybody a chance to have a little look at this one. And I wonder if anyone can suggest a strategy for working out what the times table and what the shift would be for this sequence. So if you've got pen and paper, you might want to start jotting down how you might work this out. Isabel, I can see that you've got a conjecture. It'd be interesting to know how you worked out your conjecture for what the times table and the shift are. Nine suggested a strategy to find 2 numbers which are closest together. So one thing I've seen students do with this, which is quite nice, is to rewrite the numbers in order. So I've got 50 is the smallest, I've got 68, I've got 86, I've got 122, I'm running out of space here, and I've got 248. And obviously I haven't got all the numbers there, they are in gaps, but I can start doing what Isabel has just suggested, which is to look at the difference. So from 50 to 68 is a gap of 18, from 68 to 86 is another gap of 18, but from 86 to 122,
gap of 36.
That's a gap of 36 now. But that's okay, because that means that I've just done 2 steps of 18. So I could start asking, what is the missing number between 86 and 122? And then between 122 and 248, that's a gap of
26.
And that is a multiple of 18. I know it's a multiple of 18 because it's a multiple of 9 and it's even. So I think it's worth noticing that, again, in the idea of purposeful practice, although what we might be doing is building towards nth term rules and sequences, we're also doing quite a lot of number work here and noticing properties of numbers and reinforcing some of those things. So that means that we've got the 18 times table, and then I just need to find something in the 18 times table to work out what the shift is. And Alida says that it's down by 4, and Isabel says that it's up by 14. I think both of those will work, because 14 plus 4 is 18, and that's another question that you could invite students to think about. How does the shift up and the shift down relate to each other? But yeah, if I put in the times table is the 18 times table, and shifted, what did we say, down by 4, then I get given this lovely feedback that I have got it correct there.
Before you rub anything out, Alison, I just want to point, I don't want people to go away thinking that all you need to do is find the gap between the 2 closest ones. If, for example, the gap between 86 and the next number had not been 36, if it had been 27, for example.
Okay, so if I rub out these 2 numbers and I imagine that instead I had the sequence 50, 68, 86, and then 86 plus 27, which is
113, I make it.
Okay, so in that case, I would have to think about the highest common factor of the differences, I think. And I think sometimes the computer is going to generate examples like that, where the closest gap between 2 isn't the times table.
Yes.
Okay.
Yes, I don't want, this is, I don't want people to think that you always get the situation that you got just now.
Yeah.
In a way, we were possibly a bit fortunate that that happened.
Yeah. So I think one thing that I want to say before we move on from shifting times tables is that I think this is really nice for giving students, when they are first meeting the idea of linear sequences, giving them a language to talk about linear sequences which relates to their prior understanding. So they're familiar with the idea of a times table, and so we just introduce an extra step onto that, which is the idea of a shifted times table. And they can talk about those sequences confidently by talking about what the times table is and what the shift is. But then it's just a small step for us to start introducing the notation, because we say, well, calling this the 18 times table shifted down by 4 takes me quite a long time to say, and it would take me quite a long time to write. But if I refer to the 18 times table as being the sequence 18n, so 18 times a natural number n, so it can be 18 times 1 is 18, 18 times 2 is 36, 18 times 3 is 54, and so on. And then shifted down by 4 means that I need to take away 4 from whatever I get from my answer. So the algebraic representation almost becomes a natural way of describing the language that we've used for the sequence. And given that lots of students who have feelings of anxiety towards maths commonly report algebra as being one of the things that triggers their anxiety the most, I think being able to do beginning algebra with this idea, well, it's just a shorthand to represent something that we already understand how to do with numbers, can be a way of scaffolding the entry to algebra. And then, you know, it means that whenever you see a question about nth term rules, you can refer back to it and say, well, this is just those shifted times tables that we looked at, and, you know, bring it back to something familiar.
And it might also be a nice springboard for then working on a graphical representation. And so we've got y equals 4x, and then y equals 4x is just been shifted up one. Y equals 4x minus 2 has been shifted down 2. So the shifting language is really nice when we think about it graphically. So we're relating it to the times table, like Alison is saying, which is something that they know. And eventually we end up with a graphical representation.
So a straight line graph is basically just a line through the origin that's been shifted up or down by the intercept. That's really cool. I think it took me a long time to connect why these things were called linear sequences, because the word linear didn't really mean anything to me. It was just a name given to these sorts of lines. But of course, the lines to these sequences, the lines in question are, if we change that n to an x and start plotting it, then a linear sequence is connected with a straight line graph. Or to put it another way, the graph passes through integer points, and the integer points are the ones described by the sequence. I'm going to ask you to share for the next problem, Charlie. So I'm going to stop sharing my screen for a moment. But the next problem that we want to look at is actually named after you, Charlie. So if you'd like to put it up for us. So this is Charlie's delightful machine. So tell me about your delightful machine.
Okay, can you see that?
Yeah, so there's a number 0 in a box, and there is a yellow light bulb, and it looks like there's some other light bulbs as well, but I can't see because they are switched off.
Okay, so we enter some whole numbers in the box, and there are rules of the linear sequence type that we've just been talking about that determines whether the light switches on or not. And our initial challenge is to work out what are the rules that switch the yellow, the red, the blue, and the green bulbs. And then later on, we'll add some challenges to that. Okay,
I'm going to ask everybody then to put in the chat if there is a particular number that they would like to try to see which lights it switches on. So this is pretty much what I would do in the classroom. I would invite students to suggest numbers to try to start off with. So what number should we try? Oh, 1. Okay. 7. 2.
So 1 switched the red light on. 7 switched the red and the green on. 2 switched almost all of them on.
Okay, I feel like I want to start doing some recording then. So I think what I'm going to do is I need to just annotate. So I think what I'm going to do is I'm going to write down for the red, what have I got? I've got yellow, red,
blue and green.
Blue and green. And then I'm just going to write the numbers down the side so that I can record what everything does. And I can imagine a conversation in the classroom about whether it's better to just try numbers at random or whether it might be better to work systematically. And when Charlie and I were discussing this problem before the session and I was trying numbers randomly, you got very cross with me, Charlie, didn't you? And you said, no, stop that. I want to do the numbers in order. So red, the only thing that happens with number 1 is that red is turned on and the rest of them are switched off. Okay, so for 2, I've got yellow, blue, and green. And at each stage, I might stop and ask the students, do we have enough information yet to tell us about any of the rules? So 3 does nothing. So I might put in a row of crosses just to show that I have tried it, it just didn't do anything. So 4 does yellow, and red. So I'm going to ask the question again. Does this give me information that might help me to work out the rules? If I know that they are all linear sequences, what might I be able to deduce so far? So I'm just going to give people a moment to pop into the chat if they think they can figure out anything about the sequences that we've got so far. So Nian's noticed that the evens are turning on yellow. So how could we test that conjecture? What number could we try as an example to see whether evens turn on yellow?
I'm going to try 476. There we are.
Oh, crikey. I think that's quite a nice thing to do. So I didn't say you had to try a massive number, but sometimes being able to say, can you come up with a large number, and for suitable definitions of large, it kind of shows, it's going back to what I said earlier about a generic example. You can't have sort of just done it by counting on. You have to do it by thinking structurally about it. So if I wanted to write down an nth term rule for yellow, because it's the evens, I might say, well, the even numbers, that's the 2 times table shifted by nothing. So that's the sequence 2n. Can I work out any of the other rules yet?
I think I can work out the red one.
Oh, lovely question there from Carly. What happens if you start at 0 and go down? Can we get negative numbers, Charlie? Excellent. Okay, so it looks as though we can try negative numbers as well as positive in there. So that might be a nice extension to offer some students to start working with nth term rules and testing out negative numbers that are in the sequence. Alida's asked whether red could be square numbers, and for the information that we've got so far, they are both square numbers, and so we could try something to test that conjecture. So the next square number is 9. Charlie, could you try 9 to see if it turns on the red? And it doesn't. So that's a really nice opportunity to talk about the fact that we can have a counterexample to something as a way of disproving a conjecture, as well as being able to have positive proof towards conjectures. And so
an aside, Alison, level 1, which is the only one we're going to look at today, are all linear sequences.
Yeah,
If teachers want to look at quadratic sequences, then level 2 and level 3 will deal with those. So they may get square numbers appearing at level 2 or 3. But at this stage, level 1 is a follow-up to shifting times table where we're only looking at linear sequences.
Yeah, and of course we can't say for sure what a sequence is just from knowing. If the only information we know is some numbers in the sequence, it could technically be anything. And so we do need that extra piece of information that what we are looking at is linear sequences. So I think we've got 1 more than a multiple of 3 is the other suggestion, because we've got 1 and 4. And so there's a gap of 3 between them. So I think the next thing to turn on red in that case would be 7. So could we try 7? Oh, and 7 has turned on green as well. So 7 turns on green and red. That's confirmed to me that red is the 3n plus 1 sequence, but green was turned on by 2 and by 7. So I wonder if anyone can suggest the next number that green will come on for. Carly says to try 12. Nian wants to try anything ending with a 2 or a 7. So try 12 first. And then let's do the big number thing as well. So do 397. Oh, all right, then go really big if you want. I don't know what the limits of this interactive are, Charlie, so be careful because you might try a number that will break it. But yeah, it appears that I can't even read that number. What's that? 88,876,447 does indeed turn on the green light. So 2 more than the 5 times table, a shifted times table of 5 shifted up by 2. So I can write it as 5n plus 2. And so we've just got blue to try, and Tony spotted while we were trying the negative numbers out that -2 turned on the blue, so that would make it the sequence 4n minus 2. So I think we can try some other things in that. That means that we're expecting 6 to turn on blue in that case. So can we try going up to 6? And yes, it does indeed. So I agree with that conjecture of 4n minus 2 or 4n plus 2, depending on where you are starting your sequence from. So now that we've got all of those, sometimes more than one light gets turned on at once. So a really lovely follow-up challenge is to invite students to try and find something that will turn on all 4 lights. So
and the nice thing here, Alison, I've just realized that whenever the blue light comes on, the yellow light will also come on, because the blue lights are always going to be even numbers.
Yes, because I've got 4n minus 2, that's always going to be even. And so blue and yellow always come on together. Green is 5n plus 2, so we got that ended in a 2 or a 7. So it's going to have to be one of the ones that ends in a 2. So I think we need a number that ends in a 2, that is 2 more than a multiple of 4, and 1 more than a multiple of 3. Is that right?
Yes.
Okay, we've got a suggestion in the chat from 9 that we could try 22. Hey! We've got another example of your delightful machine that I think we wanted to share.
I think 82 will also work.
Okay. Oh, how on earth did you know that?
And I think 142 might work. And so there's a question here that one could be asking about how I know.
Yes, there is. How the hell are you doing that? Oh, I think I see what you're doing.
I think 202.
So you're going up by the same amount each time, aren't you? So why are you going up by 60? Well, if I had the 2 times table, the 3 times table, the 4 times table, and the 5 times table, then 60 is the first number that appears in all of those times tables. So if I've got them shifted, then anything that turns on all 4 of those lights, if I shift it by 60, it's shifted it by all of those times tables. Yeah?
Yes.
Okay, and yeah, Alida's just expressed that in a far more concise way than I just waffled on about, to say that it's the lowest common multiple of 2, 3, 4, and 5. So that's quite nice. I think we do need to show the other example to show that it doesn't always work out as neatly as this, because this was a carefully chosen example. So we pressed refresh several times on this before the session started so that we could pick a set of 4 delightful machine numbers that we wanted. And Charlie, I know that now I don't work for Enrich anymore. I'm not supposed to make feature requests to our tech team, but if you could get the technical wizards to do a new version of this interactivity where teachers can enter the 4 rules that they want to put in advance, that would be great.
Yes, that would be great. Yes. I just wanted to we've played around with very big numbers, Alison, and part of the reason, it seems to me, is that it shows the power of what's going on here to be able to, it's part of generalizing. So for example, I think that 6,000,022 would work in this. Let me just, we didn't rehearse this. I think, haha. So being able to predict, anticipate that all the lights are going to go on shows a real understanding of lowest common multiples in this case, and generalizing. And it's not algebraic, but it's an important part of working on sequences and patterns and what we've been trying to do throughout this afternoon is trying to make sense of it in some way or another.
And yeah, and Alida's just hit the nail right on the head there, that children love to do this idea of, can you put in a really, really big number? Working with big numbers is cool. And one thing that we said when we were talking about this before the session is that you and I both get very excited about being able to do powerful stuff with maths. And I think giving students the opportunity to feel really excited and to say, that's really cool, I can do something with amazing big numbers, particularly if the start of the lesson, they're only working with very small numbers and their comfort zone is quite small, but you show them that with the power of algebra and with the power of generalizing, they can do these seemingly magical things. Could we have a quick look at the other example? Because there's a different recording strategy, which I think makes it a little bit easier to get to some of the generalization. So instead of writing down a tick for whether it turns on the light or not, I'm going to write down yellow, red, blue, and green, and every time I see one of the lights come on, I'm just going to write what number it is. So 0 turns on blue and 3 turns on blue. So I think I know that the rule for that blue is just going to be 3n. Keep going. 4 turns on yellow and green. 6 I already knew would turn on blue, so I'm not even going to write it down. 8 turns on red. 9 I knew would turn on blue. Right, 11 turns on green. So because I know it's an 11, because it's a linear sequence, that means I've got 7n plus 4. 16 turns on yellow, so that means it needs to be 12n plus 4.
So we just need red.
And red is 19, so that's 11n minus 3 or plus 8. Okay, so I don't think it's possible to turn all 4 lights on this time. I wonder if anyone else can spot why. Blue is a problem child. That's a lovely way to express it. What's the problem with the blue light here? Why is that making it impossible to turn all of them on at once? I'm going to write down the next few numbers in the yellow sequence because I think that helps to see what's going on. So let me just write that a bit further across. It was 12n plus 4, wasn't it? Yeah. So the next one will be 16 and 12 is 28. I hate having to do maths in front of an audience. I mean arithmetic. I'm very happy doing maths, just not doing arithmetic. 40 and then 52. Blue, I know, is always going to be a multiple of 3. And yellow, I think, is never going to be a multiple of 3. Because 12 is a multiple of 3, but 4 isn't. So these numbers are all one more than a multiple of 3, and that's going to carry on forever. So it's not always possible to turn on all 4 lights. Unfortunately, Charlie, we're coming towards the end of what we need to say, but I know you wanted to quickly show people how to find a couple more things on the Enrich site, and then we'll wrap up and hand back over to Patrick just to finish things off. So could you show us what you wanted to show about how to find some of these problems?
So, and again, I will put it, the links to what I'm showing you in my email, but just so that you can see how quick and easy it is to find these resources. The resources that we've shown you are our favorite resources. So we've stuck them into a curriculum mapping document. So these are the favorite enriched resources that are closely linked to the curriculum and that allow teachers to work with rich tasks, which are ideally low threshold, high ceiling. To get to this page, I just clicked on the secondary teachers button, and then I can go to the secondary curriculum page. I can click on secondary, and there's a link to a curriculum mapping document, which I clicked on earlier, and that gave me this document over here. And this document over here has section on number, but today we've been looking at the section on algebra. So that's the one that I'm going to take you to. And if I go down to the section on patterns and sequences, you'll see, let me just, we should find the problems that we've been looking at.
So there's Charlie's Delightful Machine. Yeah, I can see shifting times tables just to the left of it. In the next section there. Down, yeah.
Steel cables was a year 10 problem, so it's over here. And the other one that we looked at was 7 squares, wasn't it?
Yes.
Which I
just underneath Charlie's Delightful Machine there in the year 8 column.
And slick summing that we talked about as well.
Yeah, and I think this is really good that if you do find a problem on Enrich that you like and you find it on the mapping document, you can look at the problems, you know, either side of it and near it to find other things in the same vein. I think the only other thing that I'd like to say, well, just to wrap up some of the main ideas of what we've been trying to talk about a bit, is that patterns and sequences can be an amazingly rich opportunity to get students thinking about mathematical structure and generalizing and getting into a bit of proof, reasoning and convincing. And we know that the national curriculum focus on reasoning, fluency and problem solving means that these are all things that are being tested in exams. So even if they weren't important from a mathematical perspective, we know that the part that students tend to struggle with in the exams are those problem solving and reasoning questions. So giving them a diet of this sort of task, helping to get them confident about talking about their maths, is a really powerful opportunity. If you want to keep in touch with me and Charlie after this session, the easiest way to get in touch with Charlie is the contact details on the Enrich website. You can find me either on my website, which is alisonkiddle.co.uk, or bother me on Twitter. I'm twitter.com/AlisonKiddle will find me. But it'd be really great to hear, particularly if you use any ideas from this session in your teaching. It would be lovely to hear from you. But we're coming up on 5:30, so I'm going to hand over to Patrick just to finish off.
I'd just like to add to Alison, thank you all for participating. It's been great to work with you, and perhaps we'll get to see some of you in the summer term when we're going to be doing a similar session, but about we're going to focus on geometrical reasoning. Bye for now.
Thank you very much, Charlie, and thank you very much, Alison.